Hey everybody, this is an interview with ZisWorks, who invented a kit for certain LCD panels that brings it down to CRT levels of lag, which that alone is pretty incredible. We got pretty technical in the interview, but we talk about the different formats of LCD panels, integer scaling, and a bunch of other awesome stuff. So I'm really looking forward to getting my hands on one of these panels, and for now, I really hope everybody enjoys the interview. So here we go, an interview with Zis. Hey everybody, I'm here with Zis from ZisWorks. How's it going, man?
All right.
So I first saw your work. I think somebody linked to a Reddit post of somebody who was making a custom LCD board driver, and I was immediately just 100% on board. This is something that I've been wanting to figure out for a long time. So can you give just kind of a very short description of what your products do, just so people who might not be aware just kind of know where we're at before we get into it?
Sure. I make this little FPGA board, which drives the panel directly, as well as these DisplayPort boards that convert from DisplayPort to what's used internally, and also a power supply board, which drives the backlight in some fun ways. So that's sort of the main product. They all work together in a kit for 39-inch and 28-inch monitors. So on the workbench here, we've got one of the 39 inches being tested. It's my test bench. And yeah, they do 4K 120 hertz through dual DisplayPort inputs. They can also do increased rates up to 480 hertz if you reduce the resolution. They also do integer scaling, so they don't interpolate and make the image blurry. They'll be as true as possible to what a native resolution 1080 or 720p panel would be, and they retain the sharpness of the image. Additionally, they support, as kind of a newer feature, not complete full vertical scan out. So you can do effectively ultra wide emulation on them. So 3840 by 1440 at 180 hertz is a cool mode, and the portions at the top and bottom will be blacked out. So
wow,
it's a very versatile controller, and I mean versatile in the input sense. But it's really only meant for two panels. I've gotten lots and lots of people asking me, does this work for my panel? The answer is no, unless you have exactly the two panels that I use. The answer is no. But
so just to oversimplify, then, your boards are products that can replace the existing boards on other TVs and that are designed for gamers.
Yes. Well, not really for gamers. They can be used by them, sure, but the design intent was for engineers. So they allow very precise control over what's being displayed. So that's good for testing applications. I've had a lot of interest from game developers, from hardware developers, from companies who release other kinds of like system software for testing purposes. I've also had interest from universities for like psychology and behavioral testing. There's a very interesting list of customers.
Yeah.
And gaming is only a portion of them, and I actually kind of discourage the gaming customers in a sense, because it's really an engineering product, and it's for the people who are willing to hack things together themselves. That was the first.
That's definitely the people that are going to be listening to this podcast. So you've hit your target audience on the gamer side here.
That was the intent for the original release. We did release the X28 as a full kit not as a kit, but as a full display. So it didn't require assembly, it didn't require programming. You really just plugged it in and used it. So that one appealed more towards the gamers, but the initial release of that was still labeled as an engineering tool. Mm-hmm. Certification for sale to consumers is an ongoing project. So this is really the first run was engineering. The second run, we're in the process of building another round of boards. So stay tuned for that.
So I, for a while, worked for a company that manufactured all-in-one computers, and this was pre-iPad, so it was a little cooler to say that back then than it is now. And one of the things that I thought was kind of fascinating was that a lot of the cheap TVs actually use the same panel, and there's really only a handful of large panel manufacturers out there, at least back when I was out in Taiwan doing this work. What I always kind of I don't know if it annoyed me or not, but I don't know what the right word to say is. But basically, I would see cheap TVs that had good panels in them, but really garbage electronics, just for the point of getting a TV as inexpensively out to a customer as possible.
That's a pretty common thing still. There are fewer panel vendors now than there have been in the past. Mm-hmm.
Samsung, AUO, and then there was maybe two others that were bigger in the industry.
And LG, mm-hmm. Those are the big ones. There are certainly smaller ones like Innolux that I use. There's Sony makes panels, Sharp makes panels, Toshiba makes panels.
So the two panels that are usable with your boards, there's that Seiki 39-inch TV, which was like the first affordable 4K consumer-grade TV, right?
Yes.
Now, is that still compatible with any current panel that you could just walk into a store and buy, or do you need to hunt down that model Seiki?
So right now, the answer is you need to hunt that one down. But you can find them on Craigslist or... Yeah, usually Craigslist, you can find them for around $150. So they're pretty cheap now.
Yeah, funny, I actually gave mine to my brother, so now I'm going to have to show up at his house with like a new TCL TV and be like, bad news, I'm stealing your TV. Good news, here's a new one. So I'm definitely going to get that back to try this on there. But where does your board address the global issue of lag on flat screen TVs? Can you give a little insight into panel lag versus the electronics lag? I mean, most tech savvy people will understand that sometimes while processing an image, it'll take a longer time to get to the panel. But can you just kind of give a little bit of your insight into lag and how your board works with that? Sure.
Lag comes from a number of sources. We can consider time zero coming out of the graphics card as well.
Right.
As a you can't affect anything before then. So
yeah, I need to clarify this because I always make this mistake. In the confines, certainly in today's conversation, when I say lag, I'm talking about after the signal has left the console. And lag zero would be into a CRT that doesn't have, that is, what we all know from growing up as zero lag because the CRT itself didn't add any. So when I say lag, I'm simply talking about the lag that's added from the end of that cable into the panel. Sorry.
Yeah, and that's an important distinction to make because there is a significant amount of delay between what you want and what gets to the graphics card output. Mm-hmm. So people are overly concerned about what's on one side of this plug versus what's on the other, and sort of which side they care about most is interesting because normally the hardware people will all care about what's on the outside of the computer, mm-hmm. and the software people will only try to optimize their software. So mm-hmm. you really need both sides of this to have a good solution end to end. But from a display perspective, you've got the signal coming out of the graphics card. It's going to go into some kind of an input conversion chip mm-hmm. to be compatible with the rest of the world. Usually what happens is that there are two chips in the system. Sometimes there's more, but there's a chip that handles the input to the system. and that is designed for maximum input compatibility. And then that will go through an internal interface to the timing controller, which drives the panel. And that timing controller is purpose-built specifically for the panel that is being used. So the output of that is pretty much proprietary. The pinout's not going to be compatible with much else out there. It's usually like a one-off board, whatever's convenient for the vendor to put together quickly. Mm-hmm. And it also is group dependent. Like very similar panels from the same manufacturer might have different boards just because different groups designed them. Those boards take that panel output that's proprietary and adapt it to an input that is somewhat standard. There are a few internal interfaces used in LCDs, and there are a few enough of them that we can list, but more than enough of them that is designed. Mm-hmm. And in fact, those input chips are often made to deal with 2 or 3 kinds of outputs. So the goal is that you can kind of mix and match the input, but the T-con stays with the panel, and the T-con sets the limitations of the panel. Where does lag come into play there? Well, sometimes there are additional things in the way and additional processing going on. Everyone tries to add features to their design, and you can end up with strange things. Like you can have a panel that takes 60 hertz input, puts it through frame rate conversion, motion interpolation, and then drives the panel at 120 or 240, mm-hmm. right? And add latency, and the input controller can do nothing about it. There are some panels like that. Usually, the system input board will have the frame rate conversion. Those will also have scalers almost all the time. They can have TV tuners. A lot of them now are on Android. They're complex systems, and using all that stuff together tends to have an impact on latency. So they might buffer 2, 3, sometimes even more frames mm-hmm. in order to apply their processing stages. You know, they might want to do color correction, image sharpening. They might want to do overlays with like menus. They might want to do all kinds of other strange and wonderful things to your image in order to give what they think is the most valuable experience. And these things, while not necessarily adding lag, are often not done in a way that prioritizes it. Mm-hmm. So you can have an input board with almost no latency, but those boards are few and far between. They're normally focused on what kind of knobs can we give, what kind of features can we advertise and say that our board is better than everyone else's, so you should use our board.
I like how you put that. Those kind of features don't necessarily have to add lag, but they just sometimes end up doing it. And let's be honest, I think it's pretty much universal nowadays that your average engineer is going to aim for what they feel is the best solution, and then marketing is going to come along and be like, "That's great. So how is it going to look on the shelf at Best Buy? Let's add this other feature that the screen, the soap opera effect is what people call it sometimes." And so yeah. Mm-hmm.
Features will necessarily add lag. For example, when you have local dimming, mm-hmm. right? You can't draw that zone until you can control the output of the backlight to that zone, which means you have to have the entire data for that zone. So if you have only a few local dimming regions, you have to buffer some of the image. What's going to happen is they're not going to bother doing that. They're going to buffer the entire image, and then they're going to go through compute the backlight brightness, and then they're going to compute the image brightness, and then they're going to send both of those out. So that's a good example of an operation that does require some lag, but usually would add a lot more than required. Gotcha.
So how does your board work then? And obviously just walk us through the basics here, but from the signal in, so you have DisplayPort you're using, correct?
Yeah, so let's grab the board.
Okay.
There's one chip on there. Mm-hmm. handles the video. That one chip doesn't really have any features. That chip can convert into LVDS output, and that's its feature. It doesn't do any processing. It has a few. I think it has 2 line buffers, one for the input and one for the output. Mm-hmm. But I don't have that level of detail information on the chip. But it's a very simple chip.
And just to go off topic somewhat off topic for a second, is LVDS still the most common interface that you see for LCD panels?
No, it's not.
Okay.
LVDS is kind of an industry standard, semi-standard for many years. Mm-hmm. It's a bit of a confusing thing because LVDS, the acronym, can mean multiple things. Mm-hmm. It can mean the video format known as LVDS. With the clock over 7 and then the either 4 or 5 data lines, and then you get your non-scrambled, non-compressed, just raw pixel streaming. That's the format, and that format's pretty common, and it's dead simple. There's the electrical level known as LVDS, which is much more common. It's 1.2 volts with common mode differential signaling with, and that 1.2 is rough. You can find different implementations, and then there's a differential swing that's fairly small on top of that. There are also various modifications to it. There are things that sound similar, like mini LVDS is the output that I use. Mm-hmm. It's electrically very similar, but the bits are moved around. The clocking is simplified. Mm-hmm. And there's various reasons why those things were designed the way they are. There's kind of a newer interface for large displays called V/1, which has been getting more and more popular in the market. V/1 takes some of the disadvantages of LVDS and omits them at the expense of other issues. So V/1 is a higher speed interface. Your single wire might carry data rates that are maybe around 4 times what you would see in LVDS, and it also embeds the clock in the signal. So you have sort of one diff pair is one data lane with that, whereas with LVDS you have a clock and either 4 or 5 data lines being one lane of the interface. Mm-hmm. So V/1 is newer, faster, and fewer wires. It's also more difficult to deal with an FPGA because the data rates are high enough that you can't use the general purpose inputs and outputs of the FPGA to interface with them. They're about twice as fast as what the FPGAs can handle typically now. But they're slow enough that you need more high-speed lanes than your typical FPGA will offer. So FPGAs offer usually 2 different kinds of inputs and outputs. There's the high-speed serialized data, mm-hmm. The SERDES, and the low-speed general-purpose IOs. So you might have 4, 8, maybe even 12 lanes of the super high-speed serial lines, which the multi-gigabit, maybe you can get 12 gigabit now on a good FPGA. That's still affordable, but you only have a few of those. So if you want 4K 120 with V/1, you need 16 lanes. That's difficult to do with an FPGA because you don't have 16 of those high-speed lanes. But at the same time, you've got a data rate that's maybe 2 gigabits, 3 gigabits, and that's much more than your general I/O at like 1 or 1.5 can do. So that's V/1. And then there's MIPI, which is for phone panels and very small displays, tablets, those sorts of things. Those interfaces are super optimized for power consumption. MIPI is a packetized data stream where it's not entirely one wire. Similar to LVDS is a clock and then 4 data lanes. but the interface uses very, very low voltage signals. It's like 200 millivolts with 100 millivolt swing on top of that. Is very, very small signals. So because the signals are so small, using them with FPGAs is, you have to use an adapter in the but that's a very, there are complications with MIPI that are really intended for use with phones to reduce the number of data lanes and the power consumption. It's entirely optimized for power consumption. So
Makes sense, though.
The same wires in MIPI, one of the data lanes can be reversed, turned from a transmitter into a receiver at very low speed. So it's the bus turnaround, and there's also high speed operation and low speed operation, where the lines can be switching between these very high speed, low voltage signals, and then very low speed, like higher voltage logic that's for control signals. And like if you want to program the device before you turn on the very high speed interface, you can do that. These are features which make use with FPGAs very difficult. But
yeah,
anyway,
imagine.
Question: these interfaces are becoming more consolidated. So right now there's really just 4 interfaces for high-end panels. Like I say high-end meaning anything more complex than like a megabit or a megapixel, sorry. So you can have MIPI for small things and phones. You can have V/1 for the large TVs. You can still find LVDS in many displays. You can also find embedded DisplayPort, which embedded DisplayPort is an interesting thing. It's very common on things that don't want to have another chip between the Tcon and the source, but use sources which are not for the embedded and phone market. So this falls into the category of PC laptops, and sort of all-in-ones sort of use embedded DisplayPort. It's very similar to the regular DisplayPort. In fact, you can often make a little adapter that just converts one connector into another and use it. But you'll find EDP panels on phones, not on phones, on laptops, and typically things that are using DisplayPort outputs might use an EDP panel, because then you don't need converters. So that's sort of the space to operate with.
So with your device, let's just take something like a 1080p game console. We won't use 4K simply because we'll get back to that. But let's just take a 1080p console. Obviously, you need an HDMI to DisplayPort cable, but because it's there should be no other conversion necessary at that point, right?
If you provide a DisplayPort input, it'll work. So if you get that DP from a converter, sure.
Well, wouldn't you just need a HDMI to DisplayPort cable and not a signal converter?
No, the DisplayPort chips on this system are not DP++. They're not dual mode capable, so they only accept DisplayPort signals.
Interesting. Okay, so is that just something you could pick up from Amazon, I'm assuming, right? That's not like a pretty complicated device to buy?
Maybe. We haven't tested any of them. Some of them do exist, and the ones that I know that exist are lagless, but that's not a guarantee that everything you buy will be.
Right. So you have your 1080p HDMI source into what hopefully is a lagless converter into your input. So what happens then? It goes right into the FPGA, and you're essentially integer scaling it to match the exact signal that the panel needs in order to operate. Can you kind of elaborate a little bit on that? I might not have gotten that right either.
So there are various operations in place. The DisplayPort board converts it into LVDS. It does that with 2 line buffers, I think. I don't have insight into the chip, but there might be 1, there might be 2. Mm-hmm. There probably aren't any more than that. It's a very low-cost chip. And the block diagram, it doesn't indicate anything. And So basically that's maybe 10 microseconds of lag there. It's very minimal. So then they get converted into LVDS. LVDS is a dumb interface. It just positions bits appropriately and sends them out in a stream. The FPGA will then receive that stream. It will unpack it into, it's not really a packed thing. It will stream that data into a small memory, which is one line long. And then from that memory, it will be read at a different rate. So inside the FPGA, there's some logic to detect the minimum possible clock at which the system can operate. So it will use the input line rate to determine what the FPGA clock rate will be. So it's a decoupled system. So from that internal line buffer on the input, it goes through a very small overlay engine, which operates on a pixel by pixel basis. So that adds a clock worth of latency as the data streams through. It will add the on-screen display, which doesn't really do much right now. The on-screen display shows for the first 3 seconds when you turn it on, it will show the frame rate that you're operating at and what the panel's configured for, what the version of the firmware, and then it just hides itself. So there were some plans for the on-screen display to do additional things, but because the FreeSync support on the input chips didn't work out, we disabled it. The original intent was that the on-screen display would have a real-time graph of your frame rate, which it does, but when the inputs don't support FreeSync, you may as well disable it. But anyway, it goes through that stage, gets put into one other line buffer for the output, and the output will then read from that memory, distributing it to the various subregions of the panel, and from those subregions, the panel itself will be driven through an interface called mini LVDS, which is somewhat common on panels to talk to the chips that drive the panel itself. Because the Tcon isn't the end stage of processing. From the Tcon, there's another interface to the chips that drive the rows and columns. So one of those interfaces is mini LVDS.
And so does this also control the power boards that control the lighting and the backlight of the panel, essentially?
So for the architecture on that part of the system, the Tcon generates a sync signal that is effectively VSync if the front porch and back porch were both 0. Okay. So whenever it's not displaying an active line, the sync signal will be active. And that's there for the purpose of consistency. That sync signal will then go through the pins that come into the system. Sync signal comes out through one of these, and then it will go into our backlight driver here. When it comes into the backlight driver, it goes to this microcontroller. Source code for this is provided, so it's on GitHub. You can go and take a look at it. Please don't look too closely. So from here, we'll control our LED driver chip. And this LED driver chip is very cool because it has multiple strings with multiple PWM inputs. So that's an unusual feature. Most of them will have one PWM input that will control all strings. So I chose this chip because we can do scanning backlight, which is very, very cool. So the PWM isn't necessarily used. There is also a bunch of analog circuitry over here to control the current level of this chip. So we can modulate both the current level and the active time of each LED string in the system dynamically through a microcontroller, and we have a sync input. So there's a lot of opportunity here to program the backlight to do whatever you want. So
to add your products to a panel, you pretty much need to replace the input board, the power board, and then the LCD driver boards, right?
Yeah.
And right now you have it set up for the Seiki 39-inch, but you mentioned a second panel. Which one is that?
It's a 28-inch 4K panel from the same vendor, Innolux. The interesting thing about this panel is that it's a TN panel. So the pixel transitions are the fastest that you can get on a 4K panel, or 1 millisecond, by advertisement. You know how the panel response it's the fastest 4K panel that you can get, and it also has the backlight arranged on the side rather than the top or bottom, and the strings are arranged in segments, so you can do scanning on that. So using that panel, you get the fastest response in a scanning backlight at a low cost. So it's an excellent panel for gaming. I believe it's the best on the market right now for pure gaming when using my electronics.
So have you measured input lag from, let's call 0 from out of the console or computer, like we mentioned before, from the 0 when it hits the DisplayPort input to when when the screen is actually updated? And I do realize that the top left part of the screen is going to update microseconds faster than the bottom right, but just an overall average, what are you talking for lag to be expected with one of your kits?
So if you try to measure it using an optical response, you're not really going to get a measurement. Mm-hmm. I can tell you from the system architecture standpoint what that value will be, but we can't really measure it because the value is so much lower than the pixel response time. So unless you took apart a panel and put a probe on the electrical part of that piece of glass, you could measure it that way. But from a system standpoint, you can count the buffers. There's 2 buffers on the input chip. There's 2 buffers on the T-Con. If you're operating in dual input mode, you can have an additional 3 buffers. And there's also 1 buffer on the output. So that comes out to 6 or 7 lines. Or it comes out to between 4 and 7 lines, roughly, depending on the situation of dual input versus single input. And if you do the math with those 6 or 7 lines, it comes out to a very small number. Each line in the system is around 1/270,000th of a second. So that's how we come out to the tens of microseconds number. It does depend on the dual input versus single input thing, but it ends up being 30 microseconds is a pretty good rough number of what that latency is. And that number it's effectively 0, because when your pixel transitions on the 39-inch are advertised at 8,000 milliseconds, or 8,000 microseconds.
Microseconds, yeah.
8 milliseconds. And the transitions are much slower than that in many cases. When your transitions are that much higher than your latency, the latency is negligible.
So essentially what you're talking about in both the 28-inch and the 39-inch is a scenario where real-world performance is less than 1 millisecond of lag. So essentially it's CRT speeds.
CRTs behave differently from an optical perspective. But from the perspective of driving the pixel on a CRT versus driving the pixel on the X28, that pixel will be driven with a delay of around 30 microseconds from the time that it leaves the PC.
Yeah, I'll definitely going to go out there and say that is imperceptible by a human. As a nerd, I very rarely like to speak in definites. I usually like to say things like I feel in my testing, but I'm pretty confident in saying I doubt there's a human on the planet that would be able to detect that. Whereas there are many people out there, myself is one of them, that I can absolutely tell when there's 2 frames of lag added by the display. When I'm playing older games that are designed to be on a CRT, I can absolutely tell. All the guys in the fighting tournaments can tell. So to have something like this available for newer flat screens is pretty amazing. Would you be able to tell how much the full kit would be for both of those TVs?
Yeah, the pricing information and structuring is on my site.
Let me just bring that up real quick. So ZisWorks, and I'll just go right into your shop now. So you have you have them all broken up into the different parts. So would you be able to know just pretty much about how much it would be?
It's sort of like a menu. You can get the different flavors that you want, the different side dishes, or you can just buy the whole kit. So at the bottom, there's the full kit for the 39, the full kit for the 28. I don't want to give absolute numbers because those numbers will be going up.
Yeah, on your website here it says the first item's $140 US. I think that might be the entire or the entire thing though. So
that's oh man, I need to update this. A lot of people have gotten confused. I thought it was clear. I'm not a web designer. I'm a hardware engineer.
Yeah. Yeah, I'm a bit confused as well. So without anybody who's watching, nobody holds you to this, but like a roundabout number. Are we talking like $100 for a full kit? Are we talking $500?
So I have raised the prices since starting this. They were initially around $350, $400 for a kit shipped. That ended up being impractical. Manufacturing costs were higher than expected. Shipping costs were higher than expected.
They always are, yeah.
I was overly aggressive. I did ship the kits at that cost. I raised it later to $500 per kit, which is a little easier to swallow when it comes to how much time is involved with getting the kits ready and testing and everything. And it will probably stay around that level. I don't see it going up too much for the kits. Probably $600 is what it will be for the upcoming round. Okay. And it's the same price for both of those displays? Well, there's the kit, and then there's a fully assembled display that's tested, and you just have to plug it in. So that takes a bit more. You have to consider the cost of the panel. You have to consider the cost of the panel shipping to me and then to you. The cost of the time assembling it and testing it. If the panel fails, there's a cost there. If the panel has shipping damage or something doesn't work out, it's rejected by customs, it's lost. Those things have all happened. Even with the fairly small number of orders I dealt with before, all of those things have happened, and that wasn't accounted for in the initial pricing structure. So the cost of those full displays will go up, but they're still definitely cheaper than other similar options, which when it was originally released, there were none. Now there's the NVIDIA 27 that you can get, but that's priced at like $3K right now. Yeah. So it's definitely cheaper than that. I've increased the prices on the full displays for X28. The 39 inches are probably not going to be offered as a full display. They are. Yeah, it wouldn't make sense to ship a 39-inch panel. It's expensive to ship them around. I don't ship enough to have the same kind of discounts that the large vendors do. So shipping a 39-inch panel is pretty expensive, especially if you go internationally. It ends up being not really worth it. It costs twice as much as the item is worth to ship. Yeah. Yes, that makes a lot of sense. And because the 39-inch aren't currently in production, it just seems much easier for people to find the panel themselves, get the kit. That panel. There's an alternative. There are 40 and 42-inch variants. They use the same T-cons from the vendor. So the T-con that came with the 39 will work on the 42, and the T-con that came up with the 42 will work on the 39. I've tested that. There are no issues there. but I haven't calibrated the system. So I don't have the panel. I don't have the calibration curve because I don't have the panel, and because of that, I'm not selling it.
Makes sense. So the one thing that we didn't mention yet is how you deal with the integer scaling that you mentioned when we first started talking.
Okay. So when the video comes into the FPGA, I count the horizontal width of that video. That width is then scaled by integers. So if it's less than half the resolution of the panel, it gets scaled twice. If it's less than a third, it gets scaled 3 times. If it's less than a fourth, it gets scaled 4 times. I only support those values. Not supporting 5x or higher is because of the implementation complexity in the FPGA. It changes how the pixels are handled. With the 1, 2, 3, 4 limit, it's easy to deal with a small window.
So what's the lowest resolution that could be accepted into the panel?
I believe I have a soft limit set where the input will be disabled if it's less than like 200 pixels wide.
Oh, no, I'm talking about like 480p, 720p, like basic TV resolutions.
It'll support, I think it should support 480p. Here, we can make a custom resolution and try it.
But overall, I think most people that would be purchasing this would be running a minimum of 720p into it, although...
720p, it's the 480 hertz mode will automatically detect at 960 by 540.
Okay.
So that's 1/4 of 1080p.
Very cool. So that's the thing that, I don't want to get into the big integer scaling debate because people have a lot of thoughts on that, but it just, when it comes to video games and not TV or movies and stuff.
We didn't quite complete that discussion.
Oh, I'm sorry.
Okay, yeah. So integer scaling, the values come in, I count the horizontal extent of the image, then I stream through the image, loading it from one memory buffer into another. I replicate the pixels as necessary, and I blank out the black sides on whatever doesn't fit the panel. So if you're running it at 1600 wide instead of 1920 wide, you'll get a black border on the sides, and the image will be centered.
Very cool. That would be perfect for people running things like the open source scan converter that I have here, because I know a lot of people that would be willing to spend the money on one of your panels to be able to run classic consoles through this, which could go up to 1080p and then have it integer scaled into 4K. And this thing's got pretty great scanline support too, so you might actually be able to have something close to a CRT experience on a flat screen panel.
Yeah. So how the vertical scaling is done is a little different. Independently of replicating the pixels horizontally. And when we get that vertical scaling done, we also do it faster than we would write an individual line. So we can get increased speeds by reducing vertical resolution. So your 1080p image, instead of being limited to the 120 hertz that we can do 4K at, we can do twice as fast. So we can do 240 hertz at 1080p. And if we want to do less than 1080p, say we had 720, we can do up to 360. And at half 1080p with 540 lines tall, we can go up to 480 hertz. And this bit of magic is key to how the X28 operates, or X39. And having the horizontal scaling separate from the vertical is kind of cool, because you can also do strange things. You can give it an image that's 4K wide, but only 480 tall or something like that. So we do support 3840 by 1080. And if you do that, you're going to get rectangular pixels instead of square. Your pixels will be rectangular and tall, but you'll still have the 240 hertz rate.
So what is the number one reason that you would think for somebody to need such a fast refresh rate?
So there's engineering reasons, there are experimental reasons, and there's gaming. It's really hard to say which one is the most important for this product. All of them have been interested in these high refresh rates.
Huh. Well, from a gaming point of view, I sure as heck know where the advantages would lie, and I could only guess what the other two would be, but I'm not going to speculate because I'll probably just sound dumb. So, yeah. Well, look, I really want to get my hands on one of these. When we finish the interview, I'll talk to you about purchasing one on your next batch, but maybe you could just quickly let us know when the next batch will be available. Can people buy now and expect it to ship when they come in? Could you just give us a little insight on that?
The design files have been slightly modified from the first round. That'll be firmware compatible. So it's not like we're doing divergent branches, just minor fixes from the first round to improve, to hopefully improve some signal integrity on the panels. Some of them, there were some limits. Not all of them overclocked to 120 hertz 4K. Some of them had to do like 118 hertz 4K. Pretty much operating the panels at the edge of what they can do. So if we can make a few tweaks to get a few more percent, that'd be great. We'll see how that turns out. They certainly won't be worse than the previous ones. But firmware compatible with the old ones. We're ordering the boards probably this week. So I would expect to have boards if we rush the assembly and rush everything in 4 to 5 weeks as a reasonable time frame. Electronics take time.
Yeah.
A lot of shipping around those. There's a huge amount of logistics in just getting all the parts you need.
Oh, yeah. So basically, if somebody goes and buys one of your kits right now, they could probably expect it in 2-ish months then?
Well, I've actually disabled ordering the kits for the last 2 months. I've been working through orders from the first round, and I don't really want to start taking new orders until I've shipped all of what was previously done, sort of as a matter of principle.
Yeah, that makes sense.
The initial order page went up on, I think, the 17th of August. Orders started shipping in late December, which was already a little bit later than expected. And orders have continued to sort of trickle out. It's through May. We've still been shipping orders now. Most of it's done. There are a handful left, and I'd just like to make it up to those people to ship everything out before start taking new money.
No, that makes sense. So I guess people should just watch your website, and when something, and I'll of course let everybody know on my weekly podcast when they become open for sale, and then just go from there.
Yeah, I don't really want to do a pre-order structure this time. There's a lot of stress involved with that, and expectations of schedules and everything. I think it's a lot simpler to just front the money myself, get the boards made, have stock, and be able to ship as soon as someone orders. It's a lot less stressful for me. It's less stressful for the customer, and it's much more direct, I think.
Makes sense. Well, thank you so much for coming on. Hopefully you'll take the time to come back on after I get a chance to test one of your panels. And I'll make sure to have links to everything relevant down in the video on YouTube. Anybody that's listening audio only, check out the YouTube video for links. And we'll talk to you soon. Thank you very much, Zis. I appreciate it.
Yeah, the best place for information on this is Google Groups. It's the X28, X39 support group at Google. I'll send you a link so you can post it. There is for support and information, people posting things like, hey, I have this issue. Does anyone else have this issue? And I'll post a fix. Or people sharing calibration profiles or what they've done with it.
Cool. Sounds awesome. Thank you very much, man. I'll talk to you soon.